Suppose we have a magnet, like a north-south magnet, and it's producing a non-uniform magnetic field. We'll just draw some field lines like that. And now let's put a small current loop inside here of radius r. And what we'd like to do is we have a current I, and we like to calculate the force on this current loop. And our claim will be that if we define a symmetry axis here, call it the z-axis in our k direction, that the force on this current loop is going to be, and this current loop, remember, is a little dipole mu equals mu z k hat, where mu z is the current times the area of the dipole. The z component of the force is mu z times the gradient of the magnetic field. Now, how do we derive that? Well, let's blow up our loop for the moment here and call this the radius r. And at a point here on the loop, we have a current I, and our field line B is pointing like that. And we'll write that field. Now here I'm going to use also a r hat, theta hat, and k hat coordinate system. So it has a radial component and a component in the vertical direction. Then we know that the force dF on the current loop here is equal to the current I ds cross the B field. And so what we get is I. Now ds is in the same direction as the current. And in this case, it's our theta hat direction. So we'll write it as r d theta theta hat. And what we get is r d theta theta hat cross br r hat plus bz k hat. And when we calculate this, we have theta hat cross r hat. That's a component in the negative k hat direction. And we have theta hat cross k hat. Remember, we have r hat cross theta hat is k hat. Here we have theta hat cross k hat. And so we have a component bz r hat. Now, what this is showing us is that if we look a little carefully, the force has a negative k hat piece and a positive r hat piece. So there's a little df here. And as you go around the loop, on every side of it, there will be a little df pointing down. And so what we're seeing here is that when you add all these forces together, we'd expect this point, when we integrate over the whole loop, that this piece will integrate to 0. So this becomes 0, and that's the symmetry. The radial pieces cancel, and we're only left with this vertical piece, and that's equal to minus I r 2 pi br is the force on the wire. Now, at this moment, it doesn't quite look like our result here, but qualitatively, let's just check that the force is down. When you look in the z direction for this magnet, in this particular case, dBz dz is negative, and our dipole mu z is positive, and so we'd expect this component to be negative, and we see that agrees with our calculation here. Our next step is to see how we can apply Gauss's law for magnetism to connect these two results. When we looked at a current loop above a magnet, we discovered that the force on this wire loop was pointing downward and given by this result. Now what I'd like to do is apply our idea of conservation of magnetic flux. that for any closed surface, the magnetic flux in will be equal to the magnetic flux out. And in particular, I'd like to apply that to our magnet. So what we'll do is we don't need our current loop here anymore. And what I'm going to do is pick a equivalent of a Gaussian surface for magnetism. So I'm going to pick a little surface like this. And this surface has an area, radius r, and it's a height dz. We can call this actually, we'll call this delta z. And this is the point z, and of course up here is z plus delta z. Now, on this surface, notice that we have magnetic flux coming into the bottom face. We have magnetic flux coming out of the top face, and there's also magnetic flux coming through the sides. So this little cylinder has 3 different faces, and when we add up the flux, if delta z is very small, then on the side faces we have the radial component of the magnetic field times the area of the side face, and the area of that is 2 pi r delta z. Up here, we have flux coming out. Now, I'm going to write that as b, the z component, which is perpendicular. But remember, this is at the point z plus delta z. And that's times the area pi r squared. And here, I have flux coming in. And so that's minus b of z. But this is only at the point z times the area pi r squared. And all of that is 0. Now, I can write that as b of z plus delta z minus b of z, that's these 2 pieces. I'm going to bring this term to the other side. So that's minus br. I have 2 pi r. I'm going to divide by the pi r squared. And this delta z, I'm going to divide on that side. So this is rewriting the conservation of magnetic flux. And now you can see that in the limit, as delta z approaches 0, that this is just the partial derivative of z with respect to z. And that's equal to minus, let's write, let's bring the r upstairs and the 2 downstairs, and that's what is equal to minus br. And that is the condition of conservation of magnetic flux. And now let's apply that to our force. So we have minus I r 2 pi. Now we relate. It becomes a plus because of that minus sign, r over 2 dB dz k hat. And we can write that as r pi r squared times bz dz k hat. And you'll recognize this first piece as the magnetic moment. The second piece is that derivative k hat. And that's the force along this axis. And that's exactly what we claimed when we said that the z component of the force on a dipole in a magnetic field is equal to the z component of the dipole moment times the gradient of the magnetic field. This is a beautiful application of Gauss's law for magnetism.